modeling of mechanical systems. Mathematical modeling means that we are making the mathematical model, or we are representing the mechanical systems with the help of some equations. Mathematical equations or linear equations are involved in it, and we are representing the mechanical system with the help of some equations. So that this is in this way, if we represent a system, it is called the mathematical modeling. Okay. Now these mechanical systems, they are of two types: translational and rotational. Translational mechanical systems, they involve translatory motion, and rotational mechanical system involves rotational motion. So what is translational motion and what is rotational motion? Translatory motion means the motion which is along a straight line. This type of motion is also known as linear motion because it is along a straight line. That is why it is called linear motion. On the other hand, rotational mechanical systems, they involve rotational motion, that is motion of an object along its axis. So these are the two types of mechanical systems: translational mechanical systems and rotational mechanical systems. Now we will study the mathematical modeling of each of these mechanical systems one by one. So let us start with the translational mechanical systems. For the mathematical modeling of translational mechanical systems, we will study that how the elements of the translational mechanical systems, they can be mathematically modeled. So let us first study that what are the basic elements of a translational mechanical system. There are three basic elements. First is mass, second is spring, and third is damper. So these are the three basic elements of a translational mechanical system. Let us first study about mass. Mass is the element of the translational mechanical system which symbolizes inertia. Okay, so let us represent a mass. This is a plane surface, and on this surface a mass or an object having a mass m is placed. Now on this mass, let us first assume that this object is a ideal mass element. Ideal mass element means that it is having negligible friction and elasticity. Negligible friction and elasticity means that these two elements, spring and damper, and the effect due to these elements, it is negligible in this element. That is, this is having only the mass component in it. Okay. Now if a force F is applied on this mass in this direction, then the application of this force F, it will produce an acceleration in this mass element, and this mass element is going to be displaced from its position. Let us suppose that this displacement is given by x. So F is the force applied on the ideal mass element having a mass m. M is the mass of the object. X is the displacement which is caused due to the force applied on this mass. A is the acceleration which is produced. V is the velocity of this object, and T is the time. Okay, so this force which is applied on this mass element M, it will be given by, we know that force is equals to mass into acceleration. So mass is M and acceleration is A. So F is equals to ma. Now we know that acceleration, it is given by a equals to dv by dt. That is differentiation of the voltage with respect to, velocity with respect to time. So F is equals to m into dv by dt, where v is the velocity and t is the time. Now if we represent it in the form of displacement, then it will be F equals to m. Velocity is dx by dt, v equals to dx by dt. So it is given by d2x by dt square. So this is the relation we have obtained for the mass, that F, that is if any force is applied on this ideal mass element, then it will be equal to m d2x by dt square. Or we can say that this is the mathematical model of the element mass. Mathematical model because it is a mathematical equation or a linear equation which is representing the relationship between the force applied on the mass element and the mass of the object. So this is how we represent the mathematical model of mass. Now let us consider the second element, spring. Spring is the element which is used when we are studying the elastic concept of elastic deformation of a body. Elastic deformation means that we are stretching an object and it is coming back to its the real, it's whatever its shape, it comes back to it in real shape. So we are elastic performance that is related to a spring. Let us consider the example of spring. When we stretch the spring, it gets deformed in its shape and comes back to its original shape. So spring is related, this element is related to the elastic deformation of a body. Now let us consider an ideal elastic element. Ideal elastic element means that it is having negligible mass and damper, or negligible mass and friction. So there will be no effect of the mass element and the damper element. Negligible inertia and friction. So how we can represent an ideal elastic element? We are connecting a spring in between these 2 points. So when we apply a force, then this spring, it will be displaced from its original shape, and this displacement will be x2 and this is x1. This spring is having a spring constant k. Okay, so when we apply this force is proportional to the displacement caused in the spring. So F is the force, X is the displacement, K is the spring constant, and this spring constant, it depends upon the material which is used to make the spring. And this displacement x, it is equal to x1 minus x2. That is the position change of these 2 points. It will be x2 minus x1. So we have written that this force applied on the spring, it will be proportional to the displacement, and when we remove this proportionality sign, we will get a constant k here and x. This k is the spring constant and it depends upon the material of the spring. So the relationship for the spring between the force and the displacement is given by F equals to Kx. So in this way we can mathematically represent a spring element. Now let us study the third element, that is the damper. We know that every motion, it is opposed by friction. So if we have viscous friction in the mechanical system, that is the friction due to a liquid, or we can say that this liquid is oil. So this viscous friction, if it is introduced in the mechanical system, they give better response of the system. So damper is the element which is introducing the viscous friction in the mechanical systems. So it is related to the friction. Okay, so we know that friction, or every motion, it is opposed by friction, and viscous friction, that is friction due to a liquid, is introduced to get better response of the system. So let us consider an ideal damper, and this ideal damper will have negligible mass and we have that spring, that is elasticity. So this is the ideal damper. An ideal damper will have negligible mass and elasticity. So how we can represent a damper? Let's see. Okay, and this is the oil, and this oil is providing the friction. This is the piston. Okay, and this piston is pressing or moving inwards and pressing this liquid oil. So we are applying force here. Piston is moved inwards, so this is x1, that is the displacement in this piston, and here we have x2. Okay, so F is the frictional force, x is the displacement, x will be equals to x1 minus x2. Okay, B, it is the damping constant, and V is the velocity. So if we write the relationship between this force applied on this piston and x1 and x2, we will get that this force is equal to BV. B is the damping constant and V is the velocity. So if we put the value of the velocity in terms of displacement, we will get F equals to B dx by dt. Okay, where x is the displacement and b is the damping constant. Now if we put x as x1 minus x2, then it will be okay. So this is the relationship for a damper, and here force is equals to the damping constant and the differentiation of the difference between the two displacement. So this is the mathematical model or the mathematical representation of a damper. So the three elements of the translational mechanical systems, that is the mass, the spring and the damper, we have find out the mathematical model for all these three elements. Now if we want to find out the mathematical model of the complete translational mechanical system, then how we can do it? Let's see. So this is a mechanical translational system having all the three basic elements: a damper, a spring and a mass. This mass element is having the mass m, damper is having the damping constant as b, and spring is having the spring constant as k. And a force F is applied on this system in the downward direction, and due to this force the displacement cos, it is denoted as x. So what are the then how we can find out the mathematical model of this mechanical translational system? First we will study about a principle which is known as D. Alembert's principle. Now this principle is used for deriving the mathematical model of the physical systems. This principle states that For any body, the algebraic sum of externally applied forces and the forces resisting the motion of that body, it is equal to 0. So if we take the forces on a body, then the forces which are applied externally on that body and the forces which resist the motion of that body, their algebraic sum will be 0. That is, the total force acting on a body is 0. So we will use this principle for deriving the mathematical model. So this mechanical translational system, the external force applied on this is F, and the internal forces which are resisting its motion are due to this mass element, due to the damper, and due to the spring. So let's write all the forces acting on this system. The first force is external force. Acting on it is F, and the resisting forces are first we will have the force due to the mass. We have derived that the mathematical expression for the mass element is m d2x by dt square. That is, any force acting on a mass will be equal to m d2x by dt square. Now the resisting forces, they will be acting opposite to the external force because they are opposing the forces. So we will have minus sign here. Minus m d2x by dt square, where x is the displacement and t is the time. Now the second force is the force due to spring, and this will be equal to, again, minus sign because it is opposite to the external force F, so it will be minus kx. We have already derived it. So next we will have the force due to the damper. We can also say it as damping force. So it will also have minus sign because it is resisting the motion of the body. So minus b dx by dt. Now, according to the D'Alembert's principle, the algebraic sum of the forces acting on a body, or the algebraic sum of the external force applied on the body and the forces which are resisting the motion of the body, it is equal to 0. So, according to D'Alembert's principle, the algebraic sum will be equals to 0. So, F minus will be equals to 0. Now, if we take all these three terms to the right hand side, we will get F equals to so this is the mathematical model of a translational mechanical system involving all the forces due to the mass and the spring and the damper. So whenever we have to derive the mathematical model of a mechanical system, we will keep this formula in our mind so we can easily derive for it. Now we will study the mathematical modeling of the mechanical rotational systems. Rotational systems, they involve rotational motion. That is the motion of an object along its own axis. So the mechanical rotational system, let's see what are the basic elements of it. The First basic element is inertia. So let's derive the mathematical model for the element inertia. This inertia, it is represented by this is how we represent the element inertia, and here J is the moment of inertia, T is the torque which is applied on this element, and theta is the angular displacement, or we can say the angular rotation. Now, when a torque is applied on this element having moment of inertia J, then this element will be rotated and this angular rotation will be given by theta, and this torque will produce an angular acceleration given by alpha. So, alpha is the angular acceleration. Omega, it is the angular velocity. So this torque which is applied on this object, it is given by J and alpha. It will be equal to J alpha. J is the moment of inertia and alpha is the angular acceleration. So if we put the value of this acceleration in terms of the velocity, it will be d omega by dt. Okay. Now this angular velocity, it can be represented in the form of angular rotation or the displacement. So it will be equal to J d2 theta by dt square. Okay. So in this way we can represent a element inertia in a mechanical rotational system. It is the mathematical representation. Now let us study the second element, that is the damper. Now this damper element, it will provide the damping torque in the rotational systems. So second element will be damper and it is providing us the damping torque. So how we can represent this damper in a system? Let's see. It is the object and it is the piston, and on this piston we are applying a torque T which is producing the displacement theta 1 and having the velocity omega 1. So the second displacement will be caused is theta 2 and the velocity is omega 2. And this damping element, it is having the damping constant as B. So T is the torque, B is the damping constant, omega is the angular velocity, and theta is the angular displacement. So if we write the equation for this damper, we will get that T, that is the torque applied on this element, it is equal to B, that is the damping constant, and the difference between the two angular velocities. So if we represent it in the form of displacement, it will be d theta 1 by dt minus d theta 2 by dt. Okay. So we were having this as our torque, and it is the mathematical representation of the damper in the rotational systems. Okay, now let's study the third element, which is the spring. And spring provides us the torsional torque. Let us consider an ideal spring element. This spring is connected between 2 points A and B, and we are applying the force T is the torque, and omega 1 and theta 1 is the velocity and the displacement, and we have omega 2 and theta 2 as the final velocities and the displacement. And this spring is having the constant K. So for this we have theta is the angular displacement, K is the torsional stiffness of the spring, T is the torque which is acting on the spring, so it is the spring torque. So if we write the relationship between, for this torque applied on the spring, we will get T equals to K theta, and theta is equals to theta 1 minus theta 2. So this is the representation of the spring element, and we have studied the representation of all these three elements. So if we want to find out how we will mathematically represent a rotational mechanical systems, then we will consider all these three elements and then derive the mathematical model for the system. So let us study how we can have this. This is the moment of inertia J, and the damping torque acting on it is B, that is the damping constant. It is the surface. Torque acting on it is T, this is theta, and the torsional torque or the torsional spring constant is K. So this is a mechanical rotational system. So let's derive the mathematical model for it. So according to the D'Alembert's principle, which we have studied, that the external force, the algebraic sum of the external force and the resisting forces, it is equal to 0. So let's write the external force in this case is T, and the resisting forces are or the resisting torques, we can say, because in a rotational mechanical system, instead of force we use torque term. Okay, so resisting torques are, first we will have inertia, and inertia will be, again because these resisting forces are opposite in the direction of external force, so we will consider minus sign here. So it will be minus J dW by dt. Damping torque will be minus B d theta by dt. We can also write it in terms of theta, so that all the terms will be of same, d2 theta by dt. And here we have the spring torque as minus K theta. So if we write the equation according to the D'Alembert's principle, we will have this torque, it is T and minus J d2 theta by dt, we have square here, minus B d theta by dt minus K theta equals to 0. So if we take these three terms on the right hand side, we will get j d2 theta by dt square plus b d theta by dt plus k theta. So this is the mathematical modeling of a mechanical rotational system. So in this video, we have studied the mathematical modeling of the mechanical systems, and mechanical systems, they are of two types, translational and rotational. For translational, we have studied the three basic elements, mass, spring and damper, and for the rotational systems, we have also studied the three basic elements, mass, we can say the inertia, damper and the spring. And for all these elements, we have derived the mathematical representation or the equation, and after that we have considered a mechanical translational system and a mechanical rotational system, and for both of these systems we have derived the mathematical model. So these mathematical models, they are going to help you, this theory is going to help you to solve the questions where you have to derive the mathematical model of mechanical systems. I hope this topic is clear to you. Thank you.